object that shouldn't exist. Inside TON 618's reality-breaking secret. There's an object in the universe so massive, so incomprehensibly large, that it violates every model we have for how galaxies form and evolve. TON 618. A supermassive black hole located 10.4 billion light-years from Earth, containing the mass of 66 billion suns, compressed into a region smaller than our solar system. To put that in perspective, if you replaced our Sun with TON 618, its event horizon, the point of no return, would extend 1,300 times farther than the distance from the Sun to Earth. It would swallow Neptune's orbit. It would consume Pluto. It would reach 11 times beyond our solar system's edge into interstellar space. The black hole at the center of our Milky Way galaxy, Sagittarius A star, contains 4 million solar masses. We thought that was enormous. TON 618 is 16,000 times more massive. But mass isn't what makes TON 618 truly terrifying. It's when it exists. We're seeing TON 618 as it was 10.4 billion years ago, just 3.4 billion years after the Big Bang, at a time when the universe was barely a quarter of its current age, when galaxies were still forming, when the cosmic web was just beginning to take shape. According to every simulation, every model, every theory of black hole growth we possess, TON 618 shouldn't exist yet. Black holes grow slowly. They accrete matter gradually, even feeding at maximum theoretical efficiency, the Eddington limit. A black hole starting from a stellar mass seed at the dawn of time couldn't reach 66 billion solar masses by 3.4 billion years. The math doesn't work. The physics doesn't allow it. The timeline is impossible. Yet there it is, shining across the cosmos with the luminosity of 140 trillion suns, a cosmic impossibility that refuses to obey the rules. Today, we descend into the mystery of TON 618, the black hole that breaks cosmology. We'll explore why it shouldn't exist, what its existence tells us about the hidden violence of the early universe, and why some physicists believe it might be evidence of something even stranger, primordial black holes formed in the first seconds after the Big Bang, or dark matter collapse events that rewrote the rules of galaxy formation. What you're about to discover will challenge everything you thought you knew about the universe's history. Let's begin. Act 1. The Discovery of the Impossible. The story begins in 1957 at the Tonantzintla Observatory in Mexico. Astronomers were conducting a photographic survey of the sky, cataloging unusual objects. They designated one particular object TON 618, simply the 618th entry in the Tonantzintla catalog. At first, they thought it was a faint blue star in our own galaxy. Nothing remarkable, just another data point in an endless catalog of celestial objects. But when astronomers obtained a spectrum in 1970, measuring the wavelengths of light it emitted, they discovered something strange. The light was redshifted enormously. This wasn't a nearby star, it was something incredibly distant, racing away from us as the universe expands. It was a quasar. Quasars, quasi-stellar radio sources, are the brightest sustained objects in the universe. They're supermassive black holes actively feeding on enormous amounts of matter. As gas spirals into the black hole, it heats to millions of degrees, emitting more light than entire galaxies. TON 618 is one of the most luminous quasars ever discovered, with an absolute magnitude of -30.7. To put that in perspective, our Sun has an absolute magnitude of plus 4.8. The entire Milky Way galaxy has an absolute magnitude of minus 20.8. TON 618 is 10 times brighter than our entire galaxy. If you placed TON 618 at the distance of Andromeda, our nearest large galaxy neighbor, 2.5 million light-years away, it would appear in Earth's sky as bright as the Sun. A single black hole, as bright as our Sun, from 2.5 million light-years away. But the true shock came in 2004, when astronomers used advanced spectroscopy and gravitational modeling to estimate TON 618's mass. The numbers seemed impossible. They checked the calculations repeatedly. They questioned their assumptions. They searched for errors. But the answer remained consistent: 66 billion solar masses, with a margin of error ranging from 60 to 70 billion. This wasn't just big, this was impossible.
Here's why it's impossible. Black holes form from the collapse of massive stars, typically creating black holes of about 10 to 100 solar masses. These stellar mass black holes can grow by accreting matter from their surroundings or merging with other black holes. But accretion has a speed limit called the Eddington limit. When matter falls toward a black hole, it heats up and emits radiation. This radiation pushes outward, creating pressure that resists further infall. The Eddington limit is the maximum rate at which a black hole can accrete matter before the radiation pressure from that accretion prevents additional matter from falling in. For a black hole accreting at the Eddington limit continuously, its mass grows exponentially with a characteristic doubling time of about 45 million years. Let's do the math. Starting from a 100 solar mass stellar black hole at time 0, just after the first stars formed, perhaps 200 million years after the Big Bang, accreting continuously at the Eddington limit, how massive could a black hole become by 3.4 billion years later? 3.4 billion years divided by 45 million years per doubling is approximately 75 doublings. 100 times 2 to the 75th is approximately 3.8 times 10 to the 24th solar masses. That's enormous. Wait, let me recalculate. Actually, 2 to the 75th is about 3.8 times 10 to the 22, so 100 times 2 to the 75th, approximately 3.8 times 10 to the 24th solar masses. No, wait, that can't be right either. Let me think more carefully. Actually, there's a crucial constraint I need to include. Black holes can't accrete continuously at the Eddington limit. They need fuel, gas, and stars nearby to consume. And in the early universe, matter was more diffuse. The black hole would periodically exhaust its local supply and have to wait for more material to fall in. Realistic models suggest black holes can sustain Eddington-limited growth for perhaps 10 to 20% of the time, brief feeding frenzies interrupted by long quiescent periods. With this more realistic efficiency, starting from a 100 solar mass seed 13.6 billion years ago, you could grow a black hole to perhaps a few hundred million solar masses by the time we observe TON 1618. Not 66 billion. The shortfall is more than 2 orders of magnitude. Astrophysicists confronted an inescapable conclusion. Either our models of black hole growth are fundamentally wrong, or TON 618 didn't start from a stellar mass seed. It must have started massive, born with millions or billions of solar masses already in place, somehow, in the very early universe. But how? What could create such massive black holes so quickly after the Big Bang?
This question forced astronomers to reconsider everything they thought they knew about the first billion years of cosmic history. What they discovered was disturbing. The early universe was far more violent, far more chaotic, and far stranger than anyone had imagined. Act 2. The violent infancy of the cosmos. To understand how TON 618 could exist, we need to travel back to the universe's infancy, a time radically different from the cosmos we inhabit today. In the first few 100 million years after the Big Bang, the universe was a dark, formless void. No stars existed yet, no galaxies, just vast clouds of hydrogen and helium gas slowly collapsing under their own gravity in the densest regions. This period, called the Cosmic Dark Ages, ended when the first stars ignited, flooding the universe with light for the first time since the Big Bang's afterglow faded. These first stars, population 3 stars, were nothing like the stars we see today. They were monsters. Without heavy elements to help radiate heat efficiently, these primordial gas clouds could only fragment into very massive stars, typically 100 to 1,000 solar masses, possibly even larger. These giants burned incredibly hot, lived incredibly short lives, just a few million years, and died in spectacular supernova explosions that seeded the universe with the first heavy elements. But some of these massive stars didn't explode. They were so massive that when their cores collapsed, the implosion was unstoppable. No explosion, no supernova, just direct collapse into a black hole. This could create black holes of several hundred solar masses right away. Still not nearly enough to explain TON 618, but a better starting point than stellar remnants of a few dozen solar masses. But there's a more exotic possibility: direct collapse black holes, or DCBHs. Under certain conditions in the early universe, entire gas clouds, millions of solar masses of material, could collapse directly into black holes without ever forming stars at all. Here's how it works. Normally, when a gas cloud collapses, it fragments into many smaller clouds that form individual stars. But this fragmentation requires cooling. The cloud must radiate away its gravitational potential energy to continue contracting. In the modern universe, heavy elements and molecules like water vapor facilitate this cooling. But in the primordial universe, composed only of hydrogen and helium, cooling was much less efficient. If a gas cloud in the early universe was exposed to intense ultraviolet radiation from nearby stars, radiation strong enough to photodissociate any hydrogen molecules trying to form, the cloud couldn't cool efficiently. It would collapse as a unified mass rather than fragmenting. And if the cloud was massive enough and collapsed fast enough, it would collapse directly past the point where nuclear fusion could ever ignite. The entire cloud, tens of thousands or even millions of solar masses, would become a black hole in one catastrophic implosion. These direct collapse black holes could form with masses of 10,000 to 1,000,000 solar masses in a single event. Now we're talking about seeds massive enough to grow into TON 618 scale monsters within the available time.
Evidence for this scenario comes from computer simulations of the early universe. In 2016, researchers at Georgia Institute of Technology ran high-resolution simulations of primordial galaxy formation, including detailed modeling of radiation fields, chemical evolution, and gravitational collapse. They found that in regions where the first generation of massive stars had already formed and were emitting intense UV radiation, nearby gas clouds could indeed undergo direct collapse to black holes with masses exceeding 100,000 solar masses. The conditions were rare. Only about 1 per 1,000 proto-galaxies hosted such events. But in a universe containing trillions of galaxies, rarity still means billions of direct collapse events. But there's an even stranger possibility that takes us beyond conventional astrophysics into the realm of exotic physics: primordial black holes. What if TON 618 didn't form from collapsing matter in the early universe at all? What if it formed during the Big Bang itself, a relic of quantum fluctuations in the first fractions of a second of cosmic history? This is the primordial black hole hypothesis, and it's one of the most speculative ideas in cosmology. Here's the concept. In the first microseconds after the Big Bang, the universe was extraordinarily dense and underwent rapid expansion during cosmic inflation. During this period, quantum fluctuations, random variations in energy density, could have been stretched to macroscopic scales. In regions where density fluctuations were exceptionally large, matter could have been compressed beyond the Schwarzschild radius, forming black holes directly from the primordial plasma. These primordial black holes could have any mass, from microscopic, lighter than a grain of sand, to supermassive, millions or billions of solar masses, depending on the scale of the density fluctuation that formed them. If supermassive primordial black holes formed in the first second of cosmic existence, they would have 13.8 billion years to accrete matter and grow, more than enough time to reach TON 618's mass. The primordial black hole hypothesis has gained renewed interest because it might solve another major mystery: dark matter. We know that 85% of the matter in the universe is dark. It doesn't emit, absorb, or reflect light. We detect it only through its gravitational effects. Most physicists assume dark matter is exotic particles, WIMPs, axions, or other beyond standard model entities. But despite decades of searching, we haven't detected these particles. What if dark matter isn't exotic particles at all? What if it's primordial black holes, a sea of black holes formed in the Big Bang, pervading every galaxy, providing the gravitational scaffolding around which visible matter clusters? This would explain both dark matter and the early existence of supermassive black holes like TON 618. The hypothesis has problems. Recent observations of gravitational lensing, where light from distant objects bends around massive foreground objects, constrain the abundance of black holes in certain mass ranges. Primordial black holes can't comprise all dark matter without producing lensing effects we don't observe, but they might comprise a fraction of dark matter. And critically, the mass range where TON 618 resides, tens of billions of solar masses, isn't strongly constrained by lensing observations. TON 618 could be a primordial black hole from the Big Bang, or it could be a direct collapse black hole from the first 100 million years, or it could be the product of exceptionally efficient accretion under conditions we don't fully understand. We don't know. But all three possibilities require physics beyond our standard models of star and galaxy formation. TON 618 isn't just massive, it's a cosmic fossil, a relic of processes that operated in the universe's violent infancy, processes we're only beginning to understand. And it's not alone. Act 3. A population of impossibilities. In 2011, astronomers discovered another ultra-massive black hole in the early universe, SDSS J0100 plus 2802, containing 12 billion solar masses just 900 million years after the Big Bang. Then came J0313-1806 in 2021, a 1.6 billion solar mass black hole, existing when the universe was only 670 million years old.
In 2023, the James Webb Space Telescope began detecting dozens of early quasars powered by supermassive black holes that shouldn't exist yet, according to standard formation models. TON 618 isn't an anomaly. It's the most extreme member of an entire population of impossibly early, impossibly massive black holes. The James Webb Space Telescope's observations have been particularly revelatory. JWST can observe infrared light from the most distant galaxies, galaxies so far away that their light has been traveling toward us for over 13 billion years, showing us the universe when it was less than 1 billion years old. What JWST found shocked astronomers: massive black holes everywhere. In galaxy after galaxy from the first billion years, JWST detected the signatures of actively feeding black holes, millions to billions of solar masses. Not rare oddities, but common features of early galaxies. A 2024 study analyzed JWST data from 50 early galaxies and found that nearly 40% contained central black holes more massive than expected for their galaxy size and age. This is called the black hole overmassiveness problem. In the modern universe, there's a tight relationship between the mass of a galaxy's central black hole and the mass of the galaxy's central bulge, the spherical concentration of stars at the galaxy's core. Black holes typically contain about 0.1% of the bulge mass. But in the early universe, black holes are overmassive compared to their host galaxies, sometimes containing 1% or even 10% of the total galaxy mass. It's as if the black holes grew first, then the galaxies assembled around them. This is backwards from what we expected. We thought galaxies formed first through gravitational collapse of dark matter halos. Then black holes formed at their centers from collapsing gas and merged stellar remnants.
But the observations suggest the opposite. Black holes might have formed before their host galaxies, perhaps even seeding galaxy formation by providing gravitational wells into which gas could flow. This idea, called black hole seeding, is gaining traction among cosmologists. If supermassive black holes formed very early, either as primordial black holes from the Big Bang or as direct collapse events in the first 100 million years, they would create deep gravitational potentials, wells in space-time into which surrounding matter would fall. These black holes would act as seeds around which galaxies assemble. Rather than galaxies forming and then developing black holes would form and then galaxies would grow around them. This could explain why early black holes are overmassive. We're catching them at a phase when the black holes are already large, but their host galaxies haven't finished growing yet. TON 618 represents the extreme end of this population, a black hole that grew exceptionally massive, exceptionally fast through mechanisms we're still working to understand. Recent studies suggest TON 618 might be undergoing a phase of super-Eddington accretion, feeding faster than the Eddington limit should allow. This can happen if the accreting matter is geometrically thick and optically thin, allowing radiation to escape through holes in the accretion flow rather than pushing uniformly outward. Or TON 618 might be the product of a major black hole merger, two or more supermassive black holes colliding and combining when their host galaxies merged. If several billion solar mass black holes merged in the early universe, they could produce a TON 618 scale giant in a single catastrophic event. But these explanations still require that multiple billion solar mass black holes existed early enough to merge. The problem recurses. Where did those black holes come from?
we're forced back to the same conclusions, either primordial black holes from the Big Bang, or direct collapse events in the first few 100 million years, or physics we don't understand yet operating in the extreme conditions of the early universe. TON 618 is a cosmic mystery that refuses to resolve. Every answer leads to deeper questions. Every solution requires invoking exotic physics or unlikely scenarios. It's as if the universe is telling us, your models are incomplete. Something important is missing from your understanding of how structure forms in my early epochs. And that something might rewrite cosmology. Act 4. What TON 618 reveals about reality. TON 618 isn't just a curiosity for astrophysicists cataloging extreme objects. It's a probe of fundamental physics, a natural experiment testing our theories at energies and scales we can never reproduce in laboratories. Consider what TON 618's event horizon represents. At 1,300 astronomical units in radius, the event horizon contains a region of space larger than most stellar systems. Within that boundary, space-time is so severely warped that nothing, not matter, not light, not information, can escape. The gravitational field at the event horizon is actually quite weak, only about 1/10,000th of Earth's surface gravity. You could theoretically survive crossing it, experiencing only mild tidal forces, but you'd be doomed. Once inside, every possible future path leads to the singularity at the center, not as a matter of physical force pulling you inward, but as a matter of geometric necessity. Inside the event horizon, the singularity isn't a place in space, it's a moment in time, your future inevitably. At the singularity, our physics breaks down completely. General relativity predicts infinite density, infinite space-time curvature, infinite tidal forces, mathematical infinities that signal the theory's failure to describe what actually happens at the black hole's core. Quantum mechanics suggests something different might occur, perhaps a firewall of high-energy particles at the horizon, or a fuzzball of quantum strings replacing the classical singularity. But we don't have a complete theory of quantum gravity to make definitive predictions. TON 618's singularity, if it exists as classical general relativity suggests, contains 66 billion solar masses compressed to infinite density. That's more mass than in a small galaxy, occupying zero volume. The information paradox becomes acute. What happened to all the information about the matter that formed TON 618? Is it preserved in some quantum state or destroyed, violating fundamental principles of quantum mechanics? But perhaps the most profound implication concerns the nature of time itself. Near TON 618, time flows differently. At a distance of 2,000 astronomical units, well outside the event horizon, time runs about 0.01% slower than in flat space far from any mass. Doesn't sound like much, but it means if you orbited TON 618 at that distance for what felt like 10 years, 10 years and 36 days would pass in the distant universe. You'd return having aged less than those who stayed far from the black hole. Closer to the event horizon, time dilation becomes extreme. At twice the event horizon radius, time runs 30% slower. At 1.1 times the horizon radius, time crawls at just 10% normal speed. At the horizon itself, time stops from the perspective of a distant observer. An infalling object takes infinite time to cross the horizon, frozen forever at the boundary. But from the infalling object's perspective, time continues normally. You'd cross the horizon in finite time, experiencing nothing special at that moment. This creates a paradox. From outside, you never cross the horizon. From your perspective, you do. Both viewpoints are equally valid. Both are true in their reference frames. TON 618 reveals that time isn't absolute. It's not a universal parameter ticking uniformly throughout reality. Time is local, relative, dependent on your motion and the gravitational fields you inhabit. And at the event horizon, the very distinction between space and time becomes ambiguous. Inside the horizon, the radial direction becomes time-like. Moving inward is moving forward in time. Outside, the radial direction is space-like. You can move in or out freely. The boundary is where space becomes time. TON 618 isn't just massive, it's a laboratory for testing the most extreme predictions of general relativity, a probe of quantum gravity's mysteries, and a demonstration that the universe can create conditions so extreme they challenge the foundations of physics itself. And it formed when the universe was barely beginning. What does that tell us about the cosmos we inhabit?
Now concluding. We began by asking how TON 618 could exist, a 66 billion solar mass black hole in a universe barely 3.4 billion years old. The answer is, we don't fully know. Every explanation requires invoking exotic physics. Primordial black holes from the Big Bang's first microseconds, direct collapse of million solar mass gas clouds in the first 100 million years, super Eddington accretion under extreme conditions we've never observed directly, major mergers of multiple supermassive black holes in the early universe. None of these scenarios are impossible, but all of them push our theories to their limits. All of them require the early universe to be more violent, more extreme, more hospitable to rapid black hole growth than our standard models predict. The James Webb Space Telescope continues finding more ultramassive black holes in the early universe. Each discovery refines our understanding, but also deepens the mystery. In the next decade, next-generation gravitational wave detectors like LISA will detect mergers of supermassive black holes directly, revealing how often such mergers occur and how massive the colliding black holes are. Upcoming telescopes like the Extremely Large Telescope will probe even fainter, even more distant quasars, potentially finding black holes even more massive than TON 618 at even earlier times. Each observation constrains the possibilities, ruling out some formation scenarios while making others more plausible. But TON 618 has already taught us something profound. The universe in its infancy was radically different from the universe today. The processes that operated in the first billion years, the violence of the first stars, the collapse of primordial gas clouds, the possible abundance of primordial black holes, created conditions we're only beginning to understand. We look at TON 618 and see not just a massive black hole, but a messenger from cosmic dawn, a relic of processes that shaped the universe's large-scale structure, that seeded galaxy formation, that perhaps even comprised the dark matter binding galaxies together. The universe is vast. The mysteries remain endless. The journey continues. But TON 618 reminds us that some objects are more than curiosities. They're existential challenges to our understanding, phenomena so extreme they force us to question whether we truly comprehend the cosmos we inhabit. A black hole that shouldn't exist, exists, and in its existence lies the truth that reality is stranger, more violent, and more wonderful than we ever imagined.